Hello, and I believe the talk is beginning very soon. And my name is Qidan, and as Twitter handle FlankerQD, and here's my colleague Marco Grassi. And we are now delivering a talk on the sandboxes and how do you escape from the Chrome sandbox and the Safari sandbox, and how to have a good overview of the sandboxes. So let's get started, and here is the introduction.
I'm Marco. Hi everyone, and I'm currently a senior security researcher at KEENLAB of Tencent, and my main focus is vulnerability research, especially on OS X, iOS, and Android.
I'm also the same title. I'm not repeat again. And my main focus is on the bug hunting and exploiting on Unix and also Linux and other Linux platforms like Apple stuff. And to be honest, I know nothing about Windows. Thank you.
Thank you.
And for our team, and we are previously known as the King Team, and King Team is Pontoon a frequent winner, and I believe 8 champions in 5 or 4 years. And due to some business issues, we moved into Tencent, and we are now a deep research lab of the Tencent who develops QQ, WeChat, or whatever sort of things. And in this year, in March of this year, we got a master phone title. With the Tencent PC Manager, and I believe this is the first, and we let the Koreans go home and just beat them. Okay. So here is the agenda, and as I have stated before, and we will do an introduction to sandboxes, and both the Safari sandbox on the Apple platform and the Google Chrome sandbox on the Android platform, and we do the comparison and auditing the sandboxes. And how to do auditing, where you should look at, and we'll give some case studies on some historical vulnerabilities and some vulnerabilities we used in this year's Pontoon. And also, at the end of the talk, we'll deliver 2 demos of escaping the Safari sandboxes. And actually, I believe we should present a Chrome demo, but we hope to reserve it for this year's Pontoon, mobile Pontoon. Forgive me. And finally, we'll get to the summary and the conclusions. Okay, first.
Okay, so we will start with a quick introduction to what sandboxes are. So what is a sandbox? A sandbox is a very important concept in a modern operating system for security. So basically a sandbox is a mechanism, a way to run some code that you don't trust too much in a constrained environment. So in this way, if something goes wrong inside of this code and an attacker get, for example, code execution inside of this code, the system is not totally compromised and the adversary is still restricted inside of the sandbox. So a sandbox specifies which resource this particular program, piece of code, have access to. I think it became a crucial component for security in the last few years, after people started noticing that it's impossible to get rid of all the bugs, especially in very complex code like WebKit and web page renderers and Chrome and document parser. So it became very clear that a defense-in-depth approach must be taken.
People said the browsers are a collection of use-after-free vulnerabilities that manage to work on HTML.
And now in modern software there are 2 strategies. The first one obviously is to fix bugs, but also the second one is to constrain this untrusted code inside of sandbox. So let's take a look at a couple of sandbox implementations, and Flanker will give you an introduction to the implementation of sandbox on Android.
I believe in the historical years, people tend to adopt the DAC control. that at the beginning of Android, I believe it dates back to 2010 or 2009 when Android was originally born in a small company. And it first adopted a DSA control, and it's just enforced in the Linux kernel. At the initial version of Android, each application runs in a unique UID. And the kernel will enforce its like file access across different UIDs. For example, application with UID A, it normally cannot access files with UID B, and unless the application B specifies a word readable for his files. And I believe it's easy to understand, and any Linux beginners have a good understanding of the DSA control, that you cannot access another user's files. And in Android, each application is a user. And of course, there is an exception that is called the shared UID format. And I believe this is some special cases we need to consider, but in general, each application has a different UID, and this enforces file access and resource access. And also, Android also implements some access controls on network, and you have to be granted a specific group ID, and to access the network, to access a camera, to access some device drivers or whatever. In a conclusion, the DSA control format is very easy to understand, but it has been proven to be unflexible to deal with the modern attacks. Attackers are becoming clever and are finding more and more bugs. So people are introducing the MAC control. The MAC control is originally developed by NSA, and I believe Snowden knows that. And it's originally founded in the NSA labs, and some people adopted to the SE Android, and after like Android 4.3, it is introduced in the mainstream of Android. And this gives you the SELinux gives you a chance that you can define your own resources, or define your own policy resources, and you can enforce on whether when a resource is accessed, the policy can check, and it can tell the driver, the kernel, that you should access it, somebody should access it, or somebody should not. And only after this MAC approach is taken, and then DAC format is taken. If the MAC rejects you, you have no chance to face the DAC. And also, I believe it provides some more modern way and more elegant ways so that you can define your own SELinux policies, so that you can give a more fine-grained control of what you can do and what somebody can do and what somebody cannot. But it is becoming more and more complex as Google continues to increase the code bases for this MAC style, and it becomes somehow difficult to understand. So that's why we are also delivering this talk. And I believe on OS X, the sandboxes also takes the MAC approach from the very beginning of the iOS and some earlier like 10.7 version of OS X. So I turn to Marco.
So now that Flanker gave an overview of Android Sandbox, we will check out the OS X Sandbox for the browser. Just to give you another example so we can compare the two approach. So this is the structure of the Safari Sandbox. Basically, the Safari browser is split into multiple processes, and this is because to separate responsibility and components, and to segregate untrusted code in a less privileged process. So for our purposes, we can just think that there are two main processes. In reality, there are more, but to simplify, it's okay. One is the UI process, which is the one which the user interact on, where you click the button and go back and input URL. And the second one is in the background, and it's the web process, and it's the process responsible for rendering your web page and handling untrusted inputs, such as JavaScript and HTML and images. So, as you can understand, the web process is the one that is handling the biggest part of untrusted content, and the UI process is just in charge to manage the other process of the browser. So, Like I said, the web content process is his responsibility is to handle untrusted input and to render this untrusted input into a web page, essentially. So usually a browser compromission, like when you get initial code execution inside of the browser, you get inside this web content process because maybe you have a JavaScript bug or maybe some rendering bug or something like that. You usually get it here. But this process have a very strict sandbox. So what you need to do after to compromise the system is to escape the sandbox. And one attack surface for this sandbox is the broker interface, which is used from the web process to communicate with the UI process. Because, for example, maybe the web process must open a file, but it cannot do it himself. He must ask the broker to do it through the UI process, because the web process is too much sandboxes to do it. So the web content sandbox is implemented like any other OS X sandbox profile, and it leverages a kernel driver, which is a sandbox.txt. And there are some files, like on Android you have a SELinux profile. Also in OS X you have a sandbox definition file. And for example, for the browser renderer, you can find it at this path. And how it works, basically this file defines what are your capabilities, and whenever your code executes a system call or something like that, the kernel will check, will have some callback inside of this system call, some hooks, and then it will ask the sandbox driver to evaluate your sandbox profile, and it will say to you, yes, you are allowed, or not, you are not. So let's take a look how a sandbox profile looks like. As you can see here, we have a first very simple snippet. It's written in this custom language, very simple to understand, very human readable. And as you can see, here there is a deny default rule. So if you are under this sandbox profile, everything for you is denied, except some whitelist that will come after in the file. And as you can see, after another sandbox profile is imported, system.sb. So you need to follow into this include also to audit this sandbox profile. Recently on OS X there is also another addition that it's worth mentioning. It's a system integrity protection. So basically, on OS X, if you don't opt in for the sandbox, you are not sandboxed. But now, with the system integrity protection in a recent version of OS X, every process, even the one running as root, is running inside a global system sandbox. So it's a new security mitigation. So even if you have root code execution in user space, there are still some operation that you cannot do. As you can see here, I'm running a touch command as a root with sudo, but I cannot write into the system partition. This is because there is the system integrity protection avoiding this. So how can you bypass this? Well, the best option for an attacker is to find a kernel bug, because the system integrity protection is enforced inside of the kernel. So if you have a kernel code execution, you can also bypass system integrity protection, as we will see later in our demo.
So as you can see, with the sandboxes like SIP, after they are introduced, even the root user mode is restricted. And you cannot say that sudo make me a sandwich. No, I won't make you a sandwich. So now let's move to the Android or Google stuff. And there's a big difference between Android and iOS. Like on iOS, almost every application is sandboxed by default. But in like Google, the Android format, you should need to opt in and use the isolated process feature to handle a sandbox in your own process, and Chrome leverage this isolated process feature to implement his own sandbox. And we can see that in this Android manifest.xml file, and there's the Android isolated process equals true, and it means that this service, this org.chromium.content.app.sandboxes process service, and which runs the V8 JavaScript engine, it is isolated, and it has some different features, and there is actually very small, even no privileges for this process. We believe that the isolated process was introduced in Android around 4.3, and in the official documentation, we have a word saying that if it is set to true, the service will run a special process that is isolated from the rest of the system and no permission of its own. And given like a PS in output, we can see that the Chrome is splitted. The Chrome app is splitted into 3 processes, and there are 2 like a normal process, but there is one called Sandbox process, and we can see that it has an UID that is U0, I0, and which means isolated process 0, and it has an SELinux context that has isolated app label. So even you got a bug in the V8 JavaScript engine, and you only get a code execution in this isolated process, and you need to find some way to escape the sandbox. Otherwise, you cannot read the victims' phones, SMS. You cannot read them because the render process has no privilege. And you can use like a kernel exploit, like the ping pong route, to break out the sandbox, and also you can use the broker exploit, and also some other attack surfaces in Android, like the binder, and we will introduce later. First, if you want to find a way to break out sandboxes, you need to check its SELinux policy, and as we know, it is named like isolateapp.te, and under the external SE policy in the Android open source project's source root. And actually, to be honest, I think it's not as readable as the Apple ones. And yeah, you can see first you have the domain type, that the domain is set to isolated app for our isolated process, and then there are some allowed. By default, you are denied for all, but you have some allowed things, and you also have like a further policy to inherit from. And for some allowed policies, we can see that only 2 IPC services or 2 system services you can access it from the isolated process, which is the activity service and the display service, and you can say some unprivileged socket I/O controls, but you cannot use because after ping pong route, Google introduced this new policy to deny you from exporting these raw socket bugs, and. Yeah, and there are also some never allows. The never allows is actually not a statement in action. It's actually like a compiler directive, which means that if you accidentally enabled these things in your policy files, the SELinux 2, compiler 2 will generate an error, and they will refuse to compile it. So you can see that they have some most restricted things to deny the previous errors they have made, and we will see it later. And I know the graphic drivers have many bugs, but they explicitly specify that you cannot access graphic driver from this isolated process. But you may think that there are 2 services, like activity service and display service, you may access, but can you access all the interfaces of the 2 services? The answer is no, because there is an additional check in this interfaces. They are like enforced not isolated color, and it will actually use the binders feature to get the color. Who initialized this binder transaction, and they will retrieve the user ID that makes this call and check if you are isolated. If you are isolated or you are labeled, I'm sorry, you cannot perform it. And also, they have like a further policy, like app domain, but it's not actually quite interesting, and we may look at it in the following slides. So let's turn to you have the brief overview of how Sandbox is implemented and where you should look into the policy files. And now let's see how to audit the Sandbox profile to find the possible attack surfaces.
So how do we audit a Sandbox profile? Well, the first thing to do, obviously, is to read the definition of the Sandbox profile in order to find the best attack surfaces. Let's try to do this on the web process of Safari browser. So, as I showed you before, there is a deny default clause, but shortly after there is an import of system.sb, so we need to check that as well. And inside the system.sb, there is a nice surprise. As you can see, it's defined something called the system graphics. So we need to check that also. So system graphic is defined here, and it allows you to open several IOKit user client, all related to graphics. So basically, on OS X, the browser, the renderer process of the browser have unrestrained access to all kernel driver interfaces, which is very good because compared to Android, which you cannot access, instead here on OS X, we can access directly the graphic drivers, which is a really good attack surface, and hopefully we can find some bugs. So let's pick this attack surface of graphics in kernel. So in our Sandbox profile, this line is very interesting, which is allow IOKit open of IO accelerator. IO accelerator is the graphic driver interface into the kernel. And with this property in our Sandbox profile, we can open more than 10 IO user client and speak to the kernel, hoping to trigger some bug.
Because people like fancy graphics on their browsers, so Apple had to make decision to allow these graphics.
Yeah, for performance also.
It's tough.
Yeah. So let's see an example of vulnerability. This vulnerability, we found it last year, and we wanted to use it at Pwn2Own. But unfortunately for us, we got a bug collision, and this vulnerability was also found by Project Zero, which reported it before we could use it at Pwn2Own. So this bug was a race condition inside the external method of Apple Intel BW graphics, which is a graphic driver of almost all the most recent MacBooks. So it affects every recent MacBook with this particular CPU family, which is the newest one available for Apple products. We found it by code auditing of this code reachable from the Safari Sandbox. It was patched in 10.11.4, and it was reliably exploitable, so it was a cool bug. But like we said, it got fixed before we could use it. And it's also funny because Apple fixed it wrongly, and Flanker reported this mistake, so now the bug is properly fixed.
Previously, I believe before the day before yesterday, Apple got free bugs from everyone. And so actually they lose track of this report, although they have fixed it. And I write an email to them, and maybe after 1 month or 2 months, they assign a CV and say, "Oh, I'm sorry, we lose track of it." And I hope that after they pay bounties to everyone, they will become, they will have a more a better attitude on this sort of things.
So how this bug works very, very quickly. There is this two user client which are related to OpenGL and the OpenCL, which can be used from the Sandbox. And the problem is that who brought this driver didn't think about race condition problems. So we have some race condition problem inside the on-map user memory. So as you can see here, there are some operations performed on a EG hash table inside this external method. But as you can see, the method on this EG hash table, they are called 3 different methods sequentially. But the lock is acquired only after. So what happens if 2 threads are racing inside this function? Of course, race condition is triggered. So how to trigger it? Well, it's actually very simple to just trigger this bug, not so simple to exploit it, like we will see. In order to trigger it, you just have to open this user client and call one time or more than one map user memory to insert one element inside the hash table. And then you have to try to race with the 2 threads the call inside unmap user memory. And then you have to repeat this map and unmap race until you trigger the bug. At first, the bug will manifest itself like a double free. But as we will see after, we can turn it in something more useful.
Okay, now everyone get a record of your like data structure classes in the universities or high schools if you are a genius. And let's look at this linked list. And actually, we know that if you call the map memory, your input is maintained as a linked list, and in a hash, and the linked list is also linked on a hash table, because you know that if you use a hash table, there are hash collision issues. And this data structure solves this problem by maintaining a list on the collected elements. So we actually have like IG elements linked here, and from previous that every element has a previous pointer point to his like a brother, and he also has a nest pointer point to his nest brother. And so the ideal situation that we originally imagined that if we raise the threads, and they will pass the hash table's contains check. And when one is retrieving a pointer from this IG element, the other will freeze it, and we can fill something in this freed element and to get the RP control, to get the instruction pointer control. But in reality, we do some testing, and we find that the 2 threads they do pass this. They do pass like a contains call, but the thread 1 is like more faster, and maybe 10 meters per second faster than the second thread. And maybe there are some schedule policy issues with Apple, and the thread 1 will remove this element before thread 2 get access to this element. And the thread 2 will unfortunately hit like a null pointer dereferences. And we know that after Apple finally introduced the SMAP, and you actually cannot exploit these null pointer dereferences on their platforms. So actually, after some I believe I rehearsed my data structure classes, and I found that actually you can do race on the 2 adjacent elements, because you know that if you remove an element from a linked list, the next link to that element to this one which was removed, it will link to the previous element to the one that removed. So we can see that in this list we have element 1, 2, 3, 4, and if 2 is removed, 1 will be linked to 3, and when 3 is removed, 2 will be linked to 4. And if we raise these 2 removes at the same time, we may get 1 linked to 3, but 3 is also removed. So we get like a free element that is stably connected on this linked list. And after we call like the linked traversal, and we will hit this use after free bug, and we turn this originally double free like style like bug into a like UF bug, and this is like it is much more stable. And I believe Yanbier also found this bug, although he didn't figure out how to exploit it, at least on his blog post and project zero issues. And nevertheless, Apple fixed it, and they add a lock in this remove function, but they do not add a lock in this add function. Maybe they think there are no issues here, but actually we would like to say no to this, because if you do not lock the add function and also the unlock function, you can still we can still raise like the add function and the remove function at the same time. We can actually get a heap pointer leak to get rid of like KSLR. For example, if we are inserting an element after this linked list, because you know that if you are inserting elements after this linked list, it is get appended to the tail of the current element. So we can see that it is, if you append the element, it will be appended to the element 3, like you have, the element 3 has a next pointer point to the element 4. But if you are in another thread and you race to remove the element 3, actually you can get like a heap address in the freed element, and you can use some sort of like a memory function technique to get out of this hit pointer address in the kernel context. Yeah, so this is their partial fix, and we disclosed to Apple, and Apple fixed again, and we believe now there should be no problem. And if you are more interested in the more details, and you can check out the 2 slides, and if you are interested. Okay, now is enough time for the Apple stuff, and now look into the Android stuff. In the Android platform, that the isolated application context, it is inherited from the application policy, application.t policy, and the application.t policy inherits the domain policy. The domain policy, they have some more like complex rules, and for example, that in all domains, you can allow process to fork to get some signals, to send signal, receive signal, but actually you know that in iOS platform, a container application is not allowed to fork, although in Android it's allowed to fork. And in like the some policy, like application.t policy, we have some like ESC mem, so that you can map a portion of memory and make it executable, so that you can place a shellcode there after you get this instruction pointer control. But this is not, I believe it is going to be disallowed in this renderer process if they figure out some ways to make a GIT mitigations, just like the stuff what Apple does the day before yesterday. So we now have an understanding of these sandbox policies, and we have some options. First is the binder interface. We know that binder is the core of the Android interprocess communication, and although the binder interfaces are strictly restricted in the Chrome sandbox, we still have some ways to figure out some bugs and to get some code execution. For example, we have a bug that actually it's found, I believe, like found by last year by somebody, that it is a shared in storage integer overflow in the vector implementation of the Android libutils, and people think that it is like remote. It can be triggered in the media file parsing, but actually it can be also triggered in the sandboxes, because you know that the PACO, which is the basic transaction unit in the binder interfaces at the Java level, you can specify a class name as a string in the Java code, and when the Java object is deserialized, a class based on this string name is constructed, and you actually have an additional path to trigger the deserialization and the serialization code in the system server context. If you call the system, if you call the activity manager services interface, that from the renderer, that is accessible from the renderer sandboxes, and you make this code, you make this deserialization code called in the system server context, and actually you can trigger trigger the CVE 2015 and 3875, I'm sorry, in the system server context. And also, we believe that sometimes they forgot to do a more fine-grained lockdown on these binder interfaces. For example, in this portion of code, we found that they accidentally placed some more service handles, like the package service handle and the Windows service handle and the alarm service handle in this binder manipulation calls. So, although the renderer process cannot open these services, this function kindly open these services already for them. That the renderer sandbox process already get these 3 handles when it's initialized. So it opens like 3 additional attack surfaces. Fortunately, I believe the Google engineers are very clever, and they figure out very soon, and they patch it already, unfortunately. So after this binder stuff, we still have like some more like a Chrome IPC that you know that Marco has introduced in our previous slide that the render process have to ask the broker process, which is a more privileged process, to do something for it, and they communicated where they using the Chrome IPC. And the Chrome IPC is implemented in native code, and we believe that, and we actually, there are some bugs in it. And also, in Android platform, unlike the Windows ones, the WebGL process is running the host process. It is not running a separate process in the Chrome browser. It is running the host process, that is the Chrome browser process itself. So if we have a bug in the WebGL, just like what Lockhart do in this year and last year, we can get a code execution in the GL process, and actually we get code execution as a normal application in Android, and you get much more context to play with. And finally, we also have some like kernel stuff, just like what we did to the Safari render sandboxes. For example, the CVE 2015-1805 is a bug that is exploited by us to gain a stable routing on Android, and we try to port it to the render sandboxes. And there are good news and bad news for us to exploit it in the render sandbox. The good news is that there is no pipe policy. You know that this bug is related to the pipe IO vector in the Linux kernel, and there is no pipe policy in this isolated application, because actually it's like nobody believes that this bug is exploitable, so there is no policy for this bug in the isolated application process, and you cannot ban this very fundamental technique that is used by almost every Linux process. But I have to admit that there are still bad news, because our exploitation technique use many send MF message calls to prepare the kernel memory, but unfortunately, the render sandbox forbid you to do so. So it forces us to find some new ways to exploit, and I admit this makes our life harder. And also, you know that if you are clever, you cannot make Sam clever or your neighbor also clever, because the vendors, they always tend to make mistakes. They are always in a hurry, and they put buggy code here and there. And here is a bug in the Huawei phones, like HWEXT service that is running the system server contest. And you can see there's a very obvious integer overflow here, and you can get auto bounce access, both read and write and whatever like. But you know that Google, of course, they are not aware of these kind of interfaces. But the vendors themselves and vendors do not modify their SELinux policy to adjust to this, so they are opening also new interfaces for attack. So let's go to the comparison part.
So we analyzed the implementation of the sandbox on OS X and Android, and now we want to do some comparison and wrap up. And after this short comparison, we will do a quick demo of our OS X code execution and remote kernel code execution. And after that, we will just do some very small conclusion, and then we will conclude. So both platforms share a lot, actually. They both have a file-based sandbox profile definition, which you can audit. And but except from that, we can feel that the Chromium sandbox on Android is stronger than in other platforms, because it offers very small attack surface. And also in Android, the sandbox is more layered. Like first, you have the Chrome SELinux, the isolated app SELinux policy, and then it's running as a even if you escape this sandbox, Chrome is an application, so it's restricted by the DSC sandbox. So there are quite a lot of layers that you have to take into consideration.
So let's go to demo, and after the demo, we'll go to the conclusion. And we are presenting two demos for this year's Pontoon, and one we exploit one in the OS X.
So the two demos are both two remote compromission of OS X.
I can't find my pointer.
One is users Safari code execution bug, and then a sandbox escape in user space. And the second one is a Safari renderer bug, and then Sandbox escape to kernel. And in this demo, you will see that the victim inside the virtual machine will browse to a website, and then the attacker on the left will get a remote root shell.
This 10.11.3 is what we exploited. It is the newest version at the time of the Ponton. So first, there's the Safari renderer like a bug in the JavaScript or GSC engine. So you can see on the left side, the attacker gets a remote root shell. Because we are exporting the Windows server, which is responsible for the graphics stuff on graphics, user space graphics stuff in OS X. You can see the graphics has a freezes in the victim machine. So we choose to get an out connected root shell. So this is our user mode root exploit, and as I have said before, you have got a user mode root, but you cannot make a sandwich for you. You still need a kernel exploit. So also credit to QB for making this video. There's some fancy music. Credit to Hans Zimmer. An interesting observation is that you cannot add a user mode root to spawn a calculator. You say that a sudo calculator, it will tell you, it will not tell you, no, I will spawn a calculator output for you. It will say illegal instruction. But as a kernel mode, you can actually spawn a user mode root calculator. So if you see like a root UID calculator on your computer, oh, you are boomed.
So last slide.
So to draw a conclusion, we believe that sandboxes are great security medications. I believe that all recent advanced operating system has sandboxes support, and they take some different approaches, but they have the same concept, and they make attackers to require some additional spark to exploit sandboxes. But as a determined attacker can still compromise system, as we can see in the previous demos. So some credit goes to our colleague like Liang Chen, QB, and Wuxi, and other members of KEENLAB. So if you have questions, you can contact our Twitter, KEENLAB, and also my Twitter and Marco's Twitter.
Or you can find us around if you have any questions.
So thank you for your time.
Thank you.